Okay, so the next proof technique is going to be another direct proof style of technique, but using an equivalent form of the original statement called the contrapositive. So let's start up here. The contrapositive of P implies Q, so we're still going to be proving if-then statements, is not Q implies not P. And over here to the left, I've just shown you that these two statements are logically equivalent, which for us means if you prove the one, then you've automatically proven the other, which is sort of because they're equivalent. And so if you look at their truth tables, the P implies Q goes TF, TT, and then I have the steps for not P implies not Q, which ends up going the same way. And the only thing to notice here is that the arrow is going from not Q to not P, so really we're going from this column back to this column. So the only false we get is starting at not Q is true back to not P is false. So it's still in the second position, and all the other T's are in the same place. And the sort of, upshot, the reason we're doing this at all is that some statements are easier to prove by proving they're contrapositive. And here we have one of those statements. So all of these will say prove using the contrapositive. So maybe I'll write that. Okay, so let's look at our statement. This is if n squared is odd, then n is odd. The reason this is easier to prove by contrapositive is if we use our techniques from earlier, then the statement P is n squared is odd. And the statement Q is n is odd. And so if we start by assuming P is true, we're going to be setting n squared equals to something like 2k plus 1, and then trying to take the square root of that, and then trying to argue that that square root is still odd. The problem with that is, in general, we don't know what the square root of 2k plus 1 is. We know it does have a square root in this case because it's a square, but we don't know how to take that square root over addition and things like that. So I guess the general rule we're sort of following here is that contrapositive is better in this case because the Q statement is simpler, right? It's n is odd, and we're going to a more complicated thing, which is squaring n. And so because this number is slightly simpler than this number, that's the reason why it sort of works out better to do the contrapositive in this case. So first, let's state the contrapositive. So we're going to state not Q implies not P. Okay, so notice what Q is. Q is n is odd, so not Q is going to be equal to n is not odd, or not n is odd, we'll say. Which, in English we would say n is not odd. And the way we're going to actually use it in this statement is we're going to use the fact that all non-odd numbers are another kind, so we want to state it in sort of a positive sense. So if n is not odd is the same as saying n is even. So that's, in fact, the statement we're going to end up using for Q. And then we need to do the same thing for P. So let's write not P. And so not P is not n squared is odd. And of course, the same kind of thing's going to happen. If we said this in English, we'd say something like n squared is not odd. So that's equivalent. And then again, we use the fact that all non-odd numbers are even, and state this in a sort of positive way, which is that n squared is even. Oops. Okay, and so this is a better statement to use for not P. It's also equivalent. Okay, so let's state this contrapositive. So the contrapositive we're about to state is logically equivalent to our original statement, which is what we're really trying to prove. Okay, so the contrapositive, though, will say something like if not Q, so not Q is if n is even, then not P, and so then n squared is even. And, you know, it's not obvious if we read these two statements, maybe, that they are logically equivalent, but they are, and we can see from the truth tables and the fact that we just followed the rules exactly that this should be the statement. And so now we have if not q, which is n is even, then not p, which is n squared. Here, let me get this over. It looks like 7 is even. Okay. And then let me, so there's our not q, and there's our not p. Okay, so let's prove the contrapositive, and then by proving the contrapositive, we'll have proven the original statement. Okay, so the contrapositive is easier to prove because we're going to start off with n is even. So but now we follow the steps as before. So assume n is even, and then that'll allow us to write it using algebra. So we have a way to write this. Every even number is a multiple of 2, so 2k for some k. Now we're just going to try to get things into the form of the statement we're going to, which in this case is not p, which is the statement n squared is even. So let's square this. So if n is 2k, then n squared is 2k squared. And now what we want to say in the end is that this number is even. So the only thing we need to be able to do is factor a 2 out. I'm going to, you don't have to do this, but I'm going to multiply this all the way out just so I have a sense of what I'm working with. And then in order to say what we want to, which is that n squared is even, I need to write this as 2 times something. And so if we pull a 2 out, then what 2 times what is going to give me 4k squared? Well, the k squared's got to be there because 2's not changing that, and then 2 times 2 gives me 4, so that's it. And since 2k squared is still an integer, we have that n squared is even. And maybe we should say something in the end, like by proving the contrapositive, the original statement is true. Which is to say that the statement, if n squared is odd, then n is odd, is true. So if you know that the square of a number is odd, you know the original number had to be odd as well.